a link state request requesting full LSA information from the neighboring router. The neighboring router will send what's called a link state update, which is a packet that contains link state advertisements, and as mentioned is typically sent in response to a link state request. This contains detailed information about the link state database, rather than just an overview of it, which was contained in the database description. Link state acknowledgements acknowledge or confirm receipt of a link state update message. Now, an autonomous system is a grouping of routers under a common administrative domain. So let's assume that the routers contained within the blue portion are running ospf within a single autonomous system. They may be connecting to other routers under another administrative domain or another company's control that is running RIP, for example. ospf is an IGP, or Interior Gateway Protocol. In other words, it's used within an autonomous system. So within your organization, you may have multiple routers running ospf within the same autonomous system. For scalability, ospf networks are broken up into areas. Now there's debate about this, but Cisco would recommend never more than 50 routers within a single ospf area. In your studies in the future, you may come across different figures, but that's a good rule of thumb to use. ospf uses a hierarchical model in that you always have ospf area 0 when you have more than one area. It is possible to run ospf in another area, let's say area 1, but that's only true if you have a single area. If you've got multiple areas, you have to have area 0, which is known as the backbone area. All traffic from one area, let's say area 1, to another area, let's say area 2, will traverse the backbone. So what you do is you break up your network into multiple areas following the physical topology with the view to optimize summarization and reduce routing table updates and link state advertisements. Certain types of LSAs can be contained within an area, so the flooding of LSAs throughout the network is stopped by breaking up the network into multiple areas. Routers that border the backbone area and another area are known as area border routers, or ABRs. The three routers highlighted here are ABRs because they have one interface in area 0 and another interface in another area. One of the advantages of ABRs is that they allow for summarization of routes. If area 1 contains routes 10.110 up to 10.1.100, and in area 2 we have networks 10.2.10 up to 10.2.100, and area 3 10.3.10 up to 10.3.100, those routes can be summarized on ABRs. So you could say these 100 routes will be summarized as a single route on this ABR. So /16 mask is used to summarize these 100 routes. The same could be done here. 10.2.00/16 is a summary of these routes, and lastly 10.3.00/16 is a summary of these routes. This does require careful planning and good IP design. This router is known as an Autonomous System Border Router, or ASBR. It borders two autonomous systems. In this case we've got RIP on the left hand side and ospf on the right hand side. Even if all of these routers, including the RIP router, were within your organization, this router would still be known as an ASBR because it's connecting one routing process, RIP, to another routing process, in this case ospf. So from an ospf point of view, this is an Autonomous System Border Router. These 6 routers all have interfaces within area 0 and therefore are known as backbone routers. When traffic is sent from one area to another area, it has to traverse the backbone to reach the destination. So these 3 routers in the backbone are used to allow the traffic to flow from area 1 to area 2. ospf once again requires a good design with all areas connecting to the backbone area, as traffic flows from one area to another area through the backbone area. These highlighted routers are known as internal routers. They are internal to their specific areas. ospf routers use hellos to form neighbor relationships, or adjacencies. The hello protocol once again establishes and maintains neighbor relationships by ensuring bidirectional, in other words, two-way communication between neighbors. Bidirectional communication occurs when a router recognizes itself listed in the hello packet received from a neighbor. Hellos are sent using multicast address 224.0.0.5 and contain the following information. For neighbor relationships to be formed, it's important to remember that certain parameters have to match on both routers. Now the first field contained in a hello is the router ID. A router ID identifies this specific router and is used in various scenarios in ospf, including the election of a designated router or backup designated router. A router ID is chosen per router based on the highest IP address of any configured interface when ospf is enabled on the router, or on the highest loopback interface active on the router when ospf is enabled, or it can be manually specified using the router ID command. So to demonstrate that, you have a router, router 1. Show IP interface brief will show me the relevant interfaces on this router. Now what I'm going to do is I'm going to shut down all the interfaces and show you that ospf is not able to select a router ID if the interfaces are all shut down. So show IP interface brief again shows me that all of my interfaces are administratively shut. Now in global config mode, typing the command router, in this case ospf, and a process ID will allow me to enable ospf on this router. The process ID allows for the differentiation of multiple ospf instances running on the same router. That can become important in multi-protocol label switching environments or MPLS environments. For this course, you'll only run a single ospf process on a router, but note multiple processes can be enabled on a router. Now, notice what the router says. No router ID. ospf process 1 failed to allocate a unique router ID and therefore cannot start. Typing the command do show IP protocol shows that the routing protocol in use is ospf 1, but the router ID is 0000. ospf is not running correctly on this router. Show IP interface brief. Let's enable this interface. So interface F00, no shut. So what I'll do is I'll remove ospf and then I'll re-enable ospf. Notice there's no complaint. Do show IP protocols shows me that the router ID is 10.1.1.1. Do show IP interface brief shows me that this IP address has become the router ID. The reason why is the router ID is chosen based on the highest IP address of any active interface when the routing process is enabled. So if I enable, for instance, these two interfaces, as follows, and then type the command do show IP interface brief, you'll see that these interfaces, the fast Ethernet interface and the two serial interfaces, are up. Do show IP protocols still shows that the router ID is 10.1.1.1. I've just changed the encapsulation back to its default, so HDLC, and the interface has come up again. But what I'd like you to see is that the router ID still remains as 10.1.1.1. and I can do that command again. Do show IP protocols. Notice the router ID is 10111. I can do this command, clear IP ospf process, to clear the ospf process, and let's see if that makes any difference. So show IP protocol, and as you can see, the router ID remains the same. But if I removed ospf and then re-enabled ospf, notice the router ID has changed to 10151. So what the router has done is it looked for the highest IP address on any active interface when ospf was enabled. This time when ospf was enabled, 10151 was the highest IP address on any active physical interface, so it was chosen as the router ID. Now what happens if we enable the loopback? You'll notice the loopback has the lowest IP address. 1 is far lower than 10. So I'll no shut that. Do show IP protocol. You can see the router ID is still 10151. I'll do it again. Router ID is still 10151. But if I remove ospf and then re-enable it, notice the router ID is now 111. So the rule again, ospf router ID is chosen based on the highest IP address of any physical interface that is active when the ospf process is enabled. But if there is a loopback that is active, the loopback overrides the physical interfaces, and the loopback is used as the router ID. Loopbacks have the advantage that they never go down unless manually shut down. This has multiple advantages, including stability. If my router ID was originally 10111 and the router reloaded, assuming that there were no loopbacks enabled, the router ID would have changed to 10151. So the router ID number could have changed. But with a loopback, the router ID would remain as 111 as long as there were no other loopbacks configured on this router. So it doesn't matter what the physical interfaces are set to. It's recommended to set the router ID manually using this command and set it to a relevant loopback. In this case, I'm just going to set it to some arbitrary value to show you that you can. So I'm going to set it to 192.168.1.1, which is not an IP address on my local router. Do show IP protocol allows me to see that the router ID is 192.168.1.1. Now it's recommended practice to set the router ID to one of the loopbacks on your router. So I'm going to set the router ID to 111. As you can see here, the router ID is changed to 111. The hello packet then contains the hello and dead intervals, which must be the same on both routers. Otherwise, an adjacency or neighbor relationship will not be formed. It then contains the list of neighbors that the router knows about. That's how a router knows if there is two-way communication, because it recognizes itself in the list of neighbors that it receives in the hello packet. It then contains the area ID, which must also match on both routers. It then contains a router priority, which can be used in designated router and backup designated router elections. It then contains the designated router or DR IP address, backup designated router or BDR IP address. We're going to talk more about designated routers and backup designated routers in a moment. It then contains the authentication password. Now there are various ways to set up authentication, including clear text and MD5 hashing. We'll talk more about those later. The authentication password needs to be the same, otherwise the relationship will not be formed. And then lastly, the stub area flag needs to be the same. The stub area flag denotes whether this is a stub area or a normal area. We'll talk more about stub areas once again in later slides.